Alright, so in this video we go over section 3.6, Introduction to Functions. So in this video we are going to define what a relation is, what the domain and the range of a relation is, then identify special relations called functions, then use the vertical line test to determine whether a given graph represents a function, and find the domain and range of a function in using interval notation and set notation, and get used to function notation. So let's get started with defining relations. So what's the idea? So an equation into variables such as y equals 2x plus 1 describes the relations between the x values that we input and the y values we obtain as outputs. For example, if x equals 1, then this equation describes how to find the y value related to x equals 1. Let's see how that works. Well, x equals 1. So we are going to have y equals 2 times 1 plus 1, and the 1 is going to go right here. Okay, so if we simplify, we're going to obtain 2 times 1, which is 2, plus 1, which is 3. Alright? And this means that the point that lives in the graph of this equation is the point 1, 3. Okay, this is nothing new from what we did earlier. However, well, so in this case we are going to give it a different meaning this time. Okay, so let's do another example. For instance, for x equals 3. So if x equals 3, what is the y value? Well, y equals 2 times 3 plus 1 equals 6 plus 1 equals to 7. So that means that we are having the point 3, 7. Okay, so what is this in other words? Well, for the relationship or relation between x and y defined by y equals to x plus 1, the value, well, on the one hand, the value x is x equals, the x value of 1 is paired with the y value 3. And using a different color, the x value of 3 is paired to the value 7. Okay? So what is a relation? A relation is simply a set of ordered pairs. And then from there, the domain of the relation is the set of all first components of the ordered pairs, and the range is the range of the relation is the set of all second components in the ordered pairs. All right. So given the relation, so we're given this relation. This relation is a set of ordered pairs. This is one ordered pair, another ordered pair. So we have a few ordered pairs. Okay, determine the domain and the range. All right. So let's start with the domain. So domain, which I'm going to do in green. How are we going to find the domain? Well, the domain I'm going to highlight with green as well all the first components. By definition, the domain of the relation is the set of all first components of the ordered pairs. That is the x's, if you will. Okay, but notice how the numbers are kind of scrambled. So what we have to do is to write them from smaller to large. The smallest one is -8. Then the next one is -1, then 0, then 5, and then we have another 5. Notice we have another 5. We are not going to write it. We're not going to write it twice. And finally, the largest of them is 7. Okay. Curly brace right here. What about the range? Well, for the range, I'm going to use pink color for the y components. That is the second component of the other pairs. So range. So the range, it's going to be, well, this from smaller to large. Notice that the smallest number is this 0 right here. Notice in this case I'm looking only at the pink values. The 0 is the smallest one, and then the next one is the number 2, I believe. And notice again we have another 2 here. We have 2 number 2s. We do not repeat. We do not write repetitions. We only write them once. So 0, 2, 3, 4, 5. And I think that's about it. Okay, so let's write that as a side note. As a side note, that do not write the repetitions. Right? Just write them only once. Okay, so that's one point. The other point is to go from small to large. This is a very important side note. Okay, we need to go with that. Okay, because sometimes MyMATLAB might be a little bit picky when it comes to input the answers. If you put it twice, it may not take it. If you don't put them in order from smaller to large, it may not take it as well. Okay, so now that we know what a relation is, we're gonna look now at what a function is. And a function is a special type of relation with this particularity in which each first component in the order pairs, that is an element in the domain, corresponds to exactly one second component. Only one. All right. Let's spell this out in easier words, hopefully. Well, so this is telling us that none of the x's, the x values, are paired with more than one y value. Okay, that's one way to spell this out. Another way is to each input has only one output. If we go back to the previous page, well, notice for the input x equals 1, how many outputs did we get? Well, notice we only obtain only one output. So this equation describes a function. We're going to look at that in more detail soon. Okay. All right, so let's see. Determine the domain and range of the following sets, and also, most importantly, determine whether they are functions or not. All right, so let's see. I'm going to use green for domain again. And with the same color, I'm going to highlight the elements in the domain, that is the x values. So in this case, our x's are 1, 3, 4, and 5. 1, 3, 4, and 5. And for the range, I'm going to use pink. So the elements in the range are 3, 4, 5, 7. 3, 4, 5, 7 as well. Again, be sure to write them in ascending order. Well, in this case, the points are given nicely, so no big deal with that. Okay, now to visualize this, well, you might want to use a map. All right, a map. So I'm gonna write the domain in vertical form: 1, 3, 4, and 5. Put them in a bubble and their elements in the range 3, 4, 5, 7. Alright, so what are we going to do? So I'm going to read every single order pair. For example, the first order pair, 1, 3. This is telling me that 1 is being mapped to 3. The second order pair is telling us that the x value 3 is being mapped or paired to the value of 4. The third order pair in the set is telling us that the input x is being paired to the y value of 5, and last but not least, 5 is being paired with 7. So in this case, our conclusion is that this is a function because none of the x values, or because all x values rather, are paired or correspond from the definition, are paired with exactly 1. This is key, exactly 1 element with exactly 1 y. Okay, exactly 1 element in the y values. Let's look at the next example. So we have the set S, and we have 1, 2, 3, 4 order pairs, 4 points. Let's determine whether this describes a function. So domain with green. So for the domain, we have to highlight the x's and curly braces, the elements in the domain. So we are going to have the number 2 and then the number 3. And then notice there is another 3, but we do not write repetitions of them, and we only go with the very last one. Alright? So in this case, let's look at the range. For the range, we use pink. And what are we going to get? Well, so let's highlight the y values. We're going to have 3, 4, 5, 7. So in this case, this is really nice. 3, 4, 5, 7. Okay, so in this case, what are we going to do? To have a better visual, let's draw this as a map in vertical form. 2, 3, 4. And the range, same for the range. 3, 4, 5, 7. 3, 4, 5, 7. Okay, and we're going to study every single order pair to see if we are going to find something weird, and in this case we will. You will see. So the first order pair is telling us to make a correspondence from the 2 value, from the x value of 2 to the y value of 3. The second order pair is denoting a correspondence of the x value of 3 to the y value of 4. The third order pair is likewise denoting the corresponding between the x value of 3 and the y value of 5. And finally, The last order pair is denoting a correspondence between the x value of 4 and the y value of 7. So in this case, well, do we have a function in here? Well, in this case, it's not. In particular, the number 3 is violating the definition of a function, because in this case, well, so this relation, well, it's still a relation of points because there is a relation of values, but in this case it's not a function, because the input, or the x value, x equals 3, is paired with more than one y value. So in this case, we cannot have two x's going into two y's at the same time. Let's look at example 3. For example 3, well, this is going to be a really good example to see the difference when it is a function, when it's not a function. Well, let's take the domain first. And the domain, it's already given, it's ABC, simply ABC. Those are the elements that comprise the domain of the relation. It is yet to determine whether this relation is a function though. So range. So for the range, we have the elements 1, 2, and 3. All right. So in this case, it's not a function. As you can see, it's not a function. Not a function because, well, this element A is being mapped to more than one element in the range. Okay, this is domain and range. So let's think of this. So in this case, for case A, for this case A is being mapped to two different values at the same time. That violates the definition of range. However, on the other hand, two elements in the range can still go to the same y value. Let me give you a real life examples. For example, is it possible to be, let's see, let's say the domain represents time and range represents position or place. Is it possible to be in two different places at the same time? For example, can you be in class or at home watching this video lecture, and at the same time be in the beach, for example? Well, maybe that's possible if you take your phone or your laptop to the beach. But well, let's pretend you are in the classroom in the face-to-face, as there's no pandemic, So let's pretend that it is impossible to be in class in the classroom and at the beach at the same time. So that's why it's not a function. But now let's look at this case. Can we be at the same place at two different times? Well, this is possible. In this case, this is possible because, for example, what if you have two different classes in the same classroom? For example, you have in room 3, for example, you have room 3, one class, a philosophy class, for example, at 9 a.m. and then a math class at 11 a.m. That is possible. So we can be in the same place at two different times, but we cannot be in two different places at the same time. And this is the reason for which this is not a function. Let's look at another example. Let's determine whether each equation represents a function wall, right? So, what is this? Well, I mean, you look at an equation, yes, the slope and the intercept. Well, we're not going to analyze anything related to slopes and intercepts. We're going to talk about this in terms of a function from the function perspective. So the question is this equation representing a function? Let's find out. Okay. Let's find out what is this telling us. So x is the input and y is the output. Okay, x is the input, y is the output, and in particular this equation is describing the following: multiply the input by 3, then add 2. All right. Okay. So let's make a very quick table of values. I'm not going to do too many. We don't need to do too many. -2, 0, 2. That's enough. And y equals 3x plus 2. So y equals 3 times -2 plus 2. Y equals 3 times 0 plus 2. And y equals 3 times 2 plus 2. So in the first case, I'm going to get -6 plus 2 equals -4. In the second case, I'm going to obtain 0 plus 2, which is 2. And last but not least, this is going to be 3 times 2, which is 6, plus 2, which equals to 8. All right? So what is this going to be? This is going to give us a set of ordered pairs. So you might remember this table, we did it in the previous couple sections when we first learned how to graph linear equations. So this is going to give us the order pair -2, -4, and then 0, 2, then 2, 8. Okay. So this set of ordered pairs is going to lead us to the following: to some domain, element in the domain, element in the range. We're going to do the mappings of these two: -2, 0, 2. And in the range, -4, 2, and 8. If we do the correspondence here, well, -2 gets mapped to -4, 0 gets mapped or corresponding to 2, and 2 gets mapped or it's corresponding to 8. In this case, we can continue doing more and more and more values, but we don't need. Here we can see that with these 3, we have a function. Okay, so yes, it is a function. But why is this? Because no element in the domain corresponds to more than one element in the range. Alright, so that's the reason for which this is a function. Alright, smiley face, because it is a function. Now, letter B could look a little bit tricky because, well, if we compare example A with example B, X is the input, Y is the output. Now this function is in a way backwards in this case, because this is because of this equation being backwards in the order of the variables. Y will be the input this time, and X will be the output. So I'm going to make a quick table of values. I'm going to make a quick table of values. So like X, I'm going to take the same values, -2, 0, and +2. Okay, I'm going to evaluate this in, oh wait a minute, this is not X. This should be Y, because Y is the input in this case. So let me correct this. So Y, okay, and so X equals Y squared. So X equals -2 quantity squared. Be careful, because a negative quantity squared equals +4. X equals 0 squared is simply 0, and X equals 2 quantity squared, that's also giving us a 4. So now our job is to write the order pairs. So regardless of which one's the input, which one's the output, we still have order pairs X, Y. X goes first, and then Y. In this case, 0 goes first, that's the X, and then 0 is the Y. Finally, this 4, which is X, and that goes to 2. So let's draw this in this form of a map, domain, and range. So the elements in the domain are 4, 0, 4. Well, the smallest is 0 and the largest is 4, and we do not need to write it twice. We only write it once. Elements in the range. What are the elements in the range? -2, 0, and 2. Now let's study the correspondence of these values. So for the first point, 4, 2, that is denoting the corresponding of the input 4 towards the output -2. The second order pair 0, 0 is denoting the correspondence between the input 0 to the output 0. And the last point denotes the correspondence between the input 4 and the output 2. As you can see, the input 4 is messing things up, because 4 is mapping to two different values in the input. The input 4 maps to values in the range. Okay, so in this case, let's write it down, not a function. Not a function, because the input X equals 4. Let's use the actual vocabulary. Well, I notice I said mapping, pairing, but the correct term is corresponding. To more than one. Element in the range. One element in the range. In particular, Y equals -2 and Y equals to 2. Right? So that's why this is not a function. Sad face. This fails to be a function. Alright, letter C. Let's look at another interesting one. So every time you have an equation like this with a plus or minus symbol, you can automatically say not a function. But let's explain why is that. So consider, in this case, we don't need to make a big table like we did over here. This is going to go a lot shorter. A lot shorter. So I'm going to say not a function. Just right away. Okay, not a function. Because in this case, well, for instance, well, input x equals 2. Let's see what is going to happen. So if x equals 2, y equals plus or minus 3 times 2, which equals plus or minus 6. This means, in this case, the input x equals 2 is corresponding to two different outputs at the same time. That is, y equals negative 6 and y equals to 6. And by definition of a function, in this case, it's violating. See how this is violating the definition of a function. It's not meeting the requirements. It's mapping to more than one value in the output. It's corresponding, one element in the domain is corresponding to more than one element in the range. All right. So now let's look at functions from a different point of view. So far we have looked at functions from the point of view of ordered pairs or sets of ordered pairs. Now we have looked at equations. So now let's analyze what happens when we have graphs. And this is going to lead us to looking at the vertical line test. And what is this? So if no vertical line can be drawn so that it intersects the graph more than once, then the graph is the graph of a function. In other words, a vertical line must cross at most once. So the graph denotes or represents a function. All right. So the graph represents a function. All right. So let's look at some examples. I'm going to look at the third example, and I'm going to trace a vertical line. And in this case, well, notice how this vertical line is crossing the graph more than once. For this reason, this is not a function. Why is that? Well, if we analyze this, well, if we go to this x value of x, this x value of x is mapping one or corresponding to one and two different values. And we cannot have that. But how about number 2? If we do that, well, that only crosses once. Over here, the first one also crosses once. So this is a function. This is also a function. We already said not a function, and then not a function. All right. So that's how the vertical line test works. Well, why not a function? Well, because if you draw the vertical line look what's going to happen. Crosses more than once, crosses the graph at more than one point. Okay, so let's see, finding the value of a function, and that's going to lead us to look at function notation. Okay, so function notation. This is going to be f of x, which is exactly equals to y. Okay, and we read this, the way we read this is f of x. All right, f of x. All right. For example, like this example, in this case we have in this example we're given three functions. So the letters to denote functions, the most typical ones are f, g, and h to denote different functions. Okay. So this is called function notation, but and this is just to make the reader think that we're working in function notation. Otherwise, it would have been y equals 3x minus 5, y equals 3x squared minus 4x minus 5, and y equals 7x squared minus 3. Okay, so let's see. Given the functions, these three functions we already read, evaluate each of the following. So we need to be very careful when we look at the question. For example, they're asking us for g of 3. What are they asking us here? Need to be careful when choosing the correct function. They're asking us, this is calling for the g function, right? The g function, right? In which the input is x equals to 3. That is, all we're going to do is plug in the number 3 wherever you see the letter x, which is going to be here and here. So let's find out what's going to happen. So 3 times x squared minus 4 times parentheses minus 5. So 3 and 3. Okay, let's plug them in and be careful with the order of operations here, especially for the first term. So by PEMDAS, the exponent goes first and then the multiplication. This is going to give us 3 squared, which is 9, and then that 9 times 3, that's going to give us a 27. And then minus 4 times 3, which is 12, and then minus 5. And then combining all these numbers together, that's going to give us, so 27 minus 12, that's 15, and then minus 5, that equals to 10. All right, this is the output. This is the output. What does that mean? Well, it means this means that, and on the one hand, that the order pair, this x, the input x is being mapped to the point y, to the value of y equals 10 by the function 3x squared minus 4x minus 5. That's the order pair that lives in this function. Or another way to say this is when x equals 3, then y equals to 10. That's the two ways to interpret that result. All right, let's look at letter B. So for letter B, be very careful because this is being mapped this time. Let me see if I have another color to so I don't make a mess with colors here. So I'm gonna use, I don't want to use red, I'm gonna use this yellow right here. So this f, or kind of brown, is calling that function 3x minus 5. All right. In this case, the input is x equals to -4. So we are going to plug in the value of x equals to -4 on the function f of x wherever we see the letter x, which is going to be only here, by the way. So 3 times -5, 3 times -4. 3 times -4, that's a -12 minus 5. That's going to give us a -17. Okay, and in this case, again, this is the output. Okay, that's the output. So what about this? Well, so this means the following order pair when x equals -4, y equals to -17. And on the other hand, when x equals -4, and x equals to -4, then y equals to -17. That's what it means. Let's look at the third example right here. So h of 1. So h of 1 is calling for a totally different function. I'm going to use this purple color, like purple color, and it's calling for the function h of x. Okay, it's calling for that function. So, okay, what is that going to mean? Well, that the input x equals to -1. So it means that we are going to plug in -1 wherever we see the letter x in the function, that is only here. So 7 times quantity squared minus 3 equals, plug in -1. So be careful here when squaring negative numbers. So this is I'm going to do step by step. So 7 times -1 squared, which is +1. And then minus 3, but 7 times 1, that's a 7. Minus 3, which equals to 4. And in this case, that is the output. Okay, that is the output. What is that going to mean? Let's spell this out. So this means the order pair -1, 4. Also, this means that when x equals to -1, then y equals to 4. Okay. So this is how we talk about functions. So, well, what about this input output? Well, let's see. I have a good picture for you that I would like to do. In general, you can think as functions as machines. So something like it's just a very representative. So x equals 1, it's going to be actually I'm going to use the simple one. I'm going to use letter G. So it's going to be x equals -4. That's a -4. And in this case, f of x equals to 3x minus 5. Alright, now what are we going to do with this? Well, so we input this x equals to negative 4 to the function f of x, so f of negative 4 minus 5, and the final answer is going to be the output y equals negative 17, which is what we did, what we obtained here. So you can think of functions like machines, whose input is whatever we want to evaluate. The function that, so the machine is doing the following work or the following job. What the machine is doing is multiplying the input by 3 and then subtract 5. Whatever you obtain, that's going to be your output. And this is a very classical approach when it comes to explaining what a function is. If you read the textbook, you might run into a picture like this. Alright, so now let's see. What do we have? Let's look at functions from the point of view of a graph still, so we still have something like that. But now we're given a function, the graph of some functions with a lot of information. So from there, we're going to answer a few questions. All right, so let's see. So we have this curve, doesn't matter what the equation is, we know these particular points. Find f of 6. Okay, so f of 6, they're asking us for the output. What is the output when the input is 6? Okay, so I'm gonna go to x equals to 6. And what is the y value? What is the output? The y value, so this is input, output. The output is 0. That's it. What is the output corresponding to the input? X equals 11. Well, I'm going to go all the way to 11. And what is the y value? So this is input, and this is the output. That's a 1. And that's all we do from the graph. Okay, so for which values of x is f of x equals 0? Well, in other words, for which values of x is the output equals to 0. So, and these are going to be all the x-intercepts of the graph, or in other words, look for all the points that have a y value of 0, like this one, that one again, and that one. Alright, but in this case they're asking us for the values of x, for which y equals 0, and if we list them, negative 3 is one of them, 6 is another of them, and 10 is another of them. Final answer. What are the x-intercepts? So the x-intercepts, let's write that down here, those definitions. X-intercept point or points in which the graph crosses or touches the x-axis. And then the y-intercept analogously, oops, I was writing here, so I'll just scroll it down. The y-intercept is the point or points, point or points in which the graph crosses or touches, in this case, the y-axis. All right, the y-axis. So, and in this case, intercepts, both x and y intercepts must be expressed as order pairs. So the x-intercepts, let's list them. The first x-intercept is right here. Notice how this point is a point in which the graph crosses the x-axis, -3, 0. Another x-intercept is 6, 0. And last but not least, 10, 0. The y-intercept is point in which the graph crosses or touches the y-axis, in this case the point 0, 3. Notice these have to be expressed as order pairs, right? That's a rule of thumb. Be careful with that. All right. Let's look at last couple ones. So for what values of x does f of x equals to 3? In other words, which values of x have 3 as a y value? Okay, let's see if we have a few of those. Well, we're looking for a y equals to 3. Okay, so y equals to 3, we have this one, and we have y equals to 3 over here. So for the values of x equals 0 and x equals to 4. So let's list those. X equals 0 and 4. Those are the answers. And same, for which values of x do we have a y value of -2? Let's look back at the graph. So we have value of y equals to -2 over here and over there. So the corresponding x values are -5 and 8. And this is final answer for this. Alright, so this is pretty much the section. So this last example, number 8, I'm gonna let you do it on your own. All you have to do is just choose the correct. So what do we have? Suppose y equals f of x, and we are told that f of 3 equals 9. Based on everything that we learned when we look at this notation, you know, input, output, and all that. So which of the following statements is not true? Well, maybe this one is not true. Notice we're looking for the one that is not correct, that is not true. If you are printing these PDF files and working on them, then just circle the letter that you believe that's the one that is not right. Otherwise, if you are writing your notes on paper on your notebook, just say, all you have to do is example 8 and colon, and then just write down the letter you believe is right. Okay, so this is the end of this video of this section. I'll see you in the next video.